Hey classes, I wanted to recap a little bit about what we did today and a little bit of our data gathering that we're going to be using for the next couple of weeks to go ahead and analyze the data, extend it a little bit, especially as we talk about human body systems. So let's jump on in. If you look at the brain pop today, we did a little brain pop on mean, median, and mode, and also range. That's a good crossover with either Alderson or Wedemann's math class across the hall. We use the average most often when we're looking at the data. And what data are we using? The HW down there means homework. We had students gather data from 10 people in class, 10 for a reason, because we wanted an even number. I'll show you why in just a second. And we're checking out everyone's heart rate. And what we're going to do with the heart rate was going to find a range of the heart rate, which is what's the lowest value, what's the highest value that we had in the class, the mode, the most repeated number, and the median, the middle value. Now, the median, I put a little extra star there because with 10 data points, we don't have really a middle value. There's 5 on each side. So what you do is you take the middle 2 values and you average those. So that would be your median. A good thing came up in one of the classes today. Somebody had 2 numbers that were repeated. They had like a 2 68s and 2 72s. That's bimodal. They had 2 different modes. Sometimes it's possible not to even have a mode, but we'll talk about mode a little bit more in detail. The main ones we're going for are mean and median. So every day we're going through a different science skill. This particular skill, data analysis, we use it all the time. For example, whatever career that you're going to go into, whether it be construction management, whether you're a scientist, whether you're working retail, whether you're working in finance, you're going to be using these skills in data analysis all the time. Example, today after school, we have a teacher meeting. One of the things we're talking about at the meeting on the agenda is talking about the data breakdown to make sure that the teachers are hitting every demographic in the school. How is this age group doing? How is that age group doing? Things like that on math tests or social studies tests. It's really important because this is exactly what we do in the science world. So homework, I put a couple boxes out there. As always, figure out the mean, median, mode there. Our week started this week talking about DNA. It's been kind of a wide-ranging week. We talked about DNA in cells because we had just recently done a little bit with the organelles in a cell. And let me reach over here and show you this. This is a light microscope. If you look at the light microscopes around the room right now, the 7th grade science standards sort of shoehorn in a whole unit on light whenever we start breaking out the microscopes and we're looking at the organelles of the cell. We're using that to talk a little bit as well about a definite form of light called gamma rays. When you're looking at, say, a eukaryotic cell, you've got the DNA, for the most part, hanging out in the nucleus. We showed this a little bit ago when we were talking about viruses, for example. Viruses very, very, very tiny compared to the whole size of the cell. And high energy light waves like gamma rays can come on in. And when you've got our double helix, our DNA molecule, our deoxyribonucleic acid, you have your ATs and CGs, coding for proteins there, making genes, coding for proteins. High energy photons can come in and hit that DNA and cause mutations, cause damage. Mutations were one of our key terms because mutations are really the heart of change in biology. In other words, it's kind of like the love-hate relationship like we're going to talk about in just a second with radiation. It's a good thing and a bad thing. In other words, mutations can be very beneficial. They are very beneficial in terms of making species adapt to changes in the environment. On the flip side, mutations can also be deleterious to the organism. In other words, cause harm. By, for example, causing mutations like we're going to check out cancer, the cancer mutations that can happen when high energy photons interact with the DNA. Moving on to some of the notes that we had let me change the whiteboards here for just a sec. Our video today as I stretch to the limit of my microphone for just a moment. That looks kind of busy, but it's not too bad. If you look at the video, is called Twisting the Dragon's Tail. We didn't see all of it, but we saw most of it. Really excellent series of videos, 2 videos that go along with it by Derek Muller. We did not, again, see the whole thing, but check out his YouTube channel. It's called Veritasium. Excellent little science tidbits there. They run about 10-15 minutes. They're fun to watch. He's a great explainer of some of the more complicated issues in science. And we're talking about radiation. Again, the chapter sort of shoehorns in radiation and light there. And for us, we're interested in, one, what are the benefits of radiation, radioactivity, and what are the hazards of it? They very obviously, yesterday talked about the hazards when they were showing, for example, Pripyat in the Ukraine, the 1986 Chernobyl nuclear accident, which spread radioactive material over the then Soviet Union and also all the way up to Sweden, Norway, Finland, Denmark, Poland, Czechoslovakia. These areas had radioactive material rain down that entire city. About, I believe it was 100,000 people evacuated, and is still to this day abandoned for the most part. Obvious hazard there, but then we talked about, well, what are some of the good uses, if you will, for radiation? One of the most important ones is nuclear power, in terms of when you're looking at a nuclear power plant. There used to be one up there at Rancho Seco. There's one down in Southern California, San Onofre. You might have heard of these. When you're looking at the plumes of water vapor come out the top, water vapor isn't really a global warming gas. Remember, we talked about global warming, climate change, and global warming and climate change are human-driven in terms of us, humans, putting up carbon dioxide and methane and other greenhouse gases, but mainly carbon dioxide from burning fossil fuels. That's why I had the big chunk of coal in here the other day. Nuclear power, it does give the promise of being able to generate electricity, and we need a lot of electricity without putting out a lot of greenhouse gases. The nuclear power plant itself doesn't really put out hardly any greenhouse gases. There are greenhouse gases produced in the getting of the uranium, but the long and the short of it is, really a nuclear power plant is essentially a big tea kettle. You're taking a lot of nuclear material, usually uranium at this point, although there are some coming online that do not use uranium, and they get all this nuclear material in the same place at the same time, and it produces heat. What do we do with that heat? Well, remember our power conversions from earlier in the year? We take that heat, basically just boil water with it. And when we boil water, we get steam. Steam can turn a turbine. A turning turbine can make electricity. We also saw way back, in September, the early part of the year, the fictional account, Mark Watney, stranded on Mars. He was helping stay warm. He helped himself stay warm by using a decaying radioactive isotope, a little thermocouple, basically a radioactive battery. One of the other places, too, that we saw a positive use, if you will, of radiation is space exploration. The batteries that go on things like the Voyager spacecraft wouldn't possibly last long enough. They're just, say, a lithium-ion battery or something like that, and solar won't work that far away from the sun. You need a decaying radioactive isotope, nuclear power, to keep these spacecraft going for as long as they have to go for us to see pictures from Mars, Jupiter, Saturn, and beyond. Moving on from there, we did a leaf rubbing and a stream profile a little while ago. Can't remember if I made a video about that one, but the notes were definitely online. And we were checking out the dendritic pattern. They look like dendrites, the kind of spidering pattern that you see. That's going to come up a lot. We see it with arteries and veins. We see it with leaf patterns. We see it when we talk a little bit about the branches of the tree of evolution. In this case, we saw it as radiation was deliberately put in, technetium-99b, I believe it was put in directly to a patient. It was able to spread through the patient, and you are able to see within the patient's body because of the emission of gamma rays from a patient. For example, my pop, years ago, my dad, when he ran into a heart issue, they injected my dad with a radioactive isotope. It went up through the arteries in his heart, and you're able to get a very accurate picture of what the arteries in a person's heart, for example, are doing at that time. It's a really useful technique for imaging what's going on inside a patient. So that's a very positive use of radiation. And then also, this was a huge tie-in right here with one of the main things that we end up talking about, especially as we get into late November and then come back all the way into January, is plate tectonics. The fossil record, sedimentary rock, the rock cycle that we've touched on so far. We go in more detail to that, especially late November. And that is driven by the heat within the planet. Now, you may or may not remember, hopefully you do, that there was a lot of kinetic energy delivered to the Earth. The Earth was very hot when it was first formed 4.5 billion years ago from all the impacts asteroid impacts coming in, bringing the material that built up the early Earth. When you do the calculation, it turns out the Earth should have significantly cooled by now. And this was bugging scientists for a long time. What is keeping it so hot? Turns out radioactive decay was the missing piece to that puzzle. Radioactive decay elements that are deep within the Earth that happen to be radioactive, as they decay. Now, they're not all together like they are in a nuclear power plant, but they're spread out. But as they decay, they release some heat. That heat helps drive plate tectonics, helps keep our planet warm on the inside, driving mountain building, earthquakes, volcanoes. If it wasn't for that, if the plates were not moving, if we didn't have moving plates, the Earth would essentially be a shallow sea. There'd be no new land being built, recycled. All the materials that we need for complicated life on Earth would not be recycled into the carbon cycle, the nitrogen cycle, the rock cycle that we've already touched on a little bit. And then finally, it kind of came together at the very end when we were talking, hopefully you might remember this, the Fukushima radioactive disaster that happened, unfortunately, as a result of the 2011 earthquake off the coast of Japan. Subducting plates, again, moving continental plates, again, driven by radioactive decay, among other things. But those subducting plates caused a tsunami, and this tsunami unfortunately breached the walls, the seawalls that they had built up around the Fukushima Daiichi nuclear power plant on the east coast of Japan. And to this day, it's still releasing radiation into the Pacific. Some of this radiation, again, because of the water cycle, because of what we talked about with water constantly moving because of its kinetic energy, some of this radiation you can pick up right off the coast here at the Pacific up here. You can actually, it's actually detectable all around the Pacific Rim. But again, that was tempered with, well, it's very, very, very low levels, and we're exposed to radiation all the time. Cycles back to the beginning of the week when we talked about mutations in DNA. In other words, what causes mutations? There are several things that cause mutations, but one of the things that cause it is when high energy photons, when you've got radioactive decay, alpha particles, beta decay, or gamma rays running into DNA and causing mutations. And as we move into Darwin and the ideas of evolution, that is the critical idea. Mutations can be good, mutations can be bad, but mutations really drive forward the whole idea of descent with modifications that Darwin talks about. That's where we're going to leave it today. I know that was kind of a lot to throw into a roughly 10-minute video, but I did want to give a quick recap of where we've been and where we're going. Have yourself a great week, everyone, and I will see you in class and online. Bye-bye.